Hello, I'm delighted to have been invited to address this group. I very much appreciate the chance to address this audience. Lamento no poder estar en persona, especialmente en Buenos Aires. However, this is my last year as a dean and this is my last graduation, and I couldn't risk it. I hope that what I have prepared may be of interest to some of you. Now, let's get on with the talk. Okay, so this presentation, and we're ready to get into it, is about putting chemical engineering in the context of all engineering and the entire research university landscape. I have had the opportunity, let me just make sure in here that I get the things right. I have had the opportunity of expressing my views about the future of chemical engineering in several settings. In 2005, I was able to organize a symposium about the future of chemical engineering with these two people, Ruth Chakraborty and Pablo De Benedetti. And then subsequently, I had the opportunity of doing the institute lecture in the ICGE and present my views about the future of chemical engineering. And some of the views that I expressed at that point still hold correct, like chemical engineering is compact, coherence, especially when compared with other disciplines. And I was also able to participate in some reports that look at the future of chemical engineering. There have been several of these. The most famous was the Amundsen report in 1988. I was part of the 2007. And these were all reports about chemical engineers looking at chemical engineering. I was also part of one that was much broader, that was a group of people covering all disciplines, examining all engineering in the United Kingdom. Now, whether or not this was successful, I do not know. This was never repeated. But I wanted to use some of my experiences looking at things at this level, committees in the National Academy and so on and so forth, but also my current job as Dean of Engineering and Applied Science. I oversee these 9 departments that confer 10 different degrees, oversees a number of centers, this is a partial listing, a number of degrees, some awarded with different schools like MBAI with Kellogg. And I wanted to give a view of how chemie functions in the context of all of this. Now, I also tried to get views from people who have been looking at this from even higher altitude, like presidents of universities. There are a number of chemists who became presidents of universities, like Bob Brown, Ken Keller, and Eric Kaler. They were all from Minnesota, chemical engineering. And so I seek their views. Also, people like Ed Kassler, who became president of the ICG, and also people like Pablo De Benedetti from Princeton, Ed Glant from UPenn. These two gentlemen, by the way, were from Argentina. And just to be able to really fulfill the promise of the title, which is chemical engineering in the context of all engineering and the entire research landscape. So I will cover a few things. But we will start with how disciplines advance before going into what's contained in chemie, a bigger lens, the interplay between science and technology. So how disciplines advance? Disciplines advance, this is a classic image from a paper in Harvard Business Review many years ago. And disciplines become larger, and as they become larger, there's a series of drivers and a series of crises. The drivers could be initially creativity, then direction, delegation, coordination, and there are crises in between, crisis of control, because the things become very big, red tape, and so on. So in the context of engineering, chemical engineering, it's pretty clear. As chemie grew, they were domains that at some point wanted to get in chemie. They had to fight for acceptance. And at some point, we had to try to keep them in because they were trying to move out. The domains that I'm talking about was material science. Initially, we're talking about the 70s, 80s, biology. And some things have split. For example, departments like electrical and computer engineering may have become two departments. In some cases, they gave birth to computer science. In many cases, chemie gave birth to biomedical engineering, and so on. So, but at the moment, chemie covers probably the widest range of length scales, from Armstrongs to hundreds of kilometers, from nano to environmental problems, atmospheric science, and time scales from femtoseconds, like in catalysis, to hundreds, even thousands of years, possibly with forever chemicals. So the fact that chemies cover a wide range of territories, you can see when you look at who chemies collaborate with. So this is a representation of who chemies collaborate with from my own institution. In this case, you can see chemies collaborating with two departments in the medical school, the yellow dots, three other departments in engineering, a few departments in art and science. By the way, this is all extracted from publications on ISI, and this was done actually by one of my former PhD students and another colleague. They formed a company that eventually was acquired by IDO. And this is 2005. And if you look at chemie a few years back, a much richer set of collaborations. They collaborate with all the departments in engineering, except industrial at that point, with many more departments in the medical school. And you can also take a look at inside the school. For example, Dashun Wang, one of my colleagues, did this collaboration diagram. You can see by different colors, different departments clustered in some way. Green represents electrical and computer engineering, but not all of the greens are lumped together. And as you go on, the network becomes richer, and by 2019, is far richer in here. You can, in this network, reach any other part of the network 84% of the time. And on average, there are people who do not collaborate with anybody. So for example, the little dots on the periphery may be young faculty who have not yet been able to set a foot in the place, and they have yet to develop collaborations. But on the average, everybody collaborates with about 5 people. And in here you see this a little bit more zoomed. I highlighted is the brownish with the green edge is chemical engineering. In here you see it a little bit better. And this is a picture in chemie. And so this is the current structure. Now, what gave rise to the structure? What's the driver for this? Well, the driver is, in some sense, what you see here, which is the sources of funding. The sources of funding in chemie, in general, in almost every chemie department, are highly diversified. You see 15%, which is NIH, 18% Department of Defense, DOE, foundations, industry, as opposed to, I don't know, the medical school is mostly NIH funding. Now, it's hard to do research without funding. So funding drives research areas and collaboration, and it's hard to collaborate without support. A way to alter this equilibrium is by giving catalyst grants in which you could say you will fund things that involve two different schools, and you use this as seed grants, and we monitor the research, and we see the return of investment. this is something really a good thing if you can afford to do it. Now, we recognize that funding drives research and collaboration, but also that research and collaboration, some key people in your institutions drive funding. In fact, where do agencies get ideas from? Is from some of us. So for example, the idea of NSF and convergence, which is something that we have been doing for a while, originated with someone proposing the idea. So let's go to one thing that has to do with all the composition of thinking in a school of engineering, the modes of thinking, what is contained in engineering. So let's start with these three domains, which are the largest three domains accumulated creativity in humanity: science, technology, and art. And if you want to assign a verb to science, you put discover, technology, invention, art, creation. And in science, the biggest discovery of science is science itself, really. But the scientific method really controls things when you are dealing with experimental work. In theoretical work, is more about induction and sweeping generalizations. And there were no experiments done in the moon before Newton proved how the moon would move under gravitation, for example. So where does math, for example, which is part of engineering, fit? You will say that math probably fits in discovery and part in creation. Many mathematicians will argue that mathematicians just discover what is out there, so I put them both in art and creation. But applied math fits in technology. A lot of applied math is invention. What is computer science? Well, the theory parts more in like math, like pure math, but it's also invention, and I put creation in there because some people in computer science, this book is one of them, will argue that there is a lot of commonality of thought in between artists and people who do coding, for example. Engineering clearly fits span science and technology, but engineering also contains elements of artistic components, so you'll put creation. And you would argue, and this book was one of the ones who argued, that engineering thinking is probably the oldest type of thinking in the world. That if you ever face a problem with incomplete information and under constraints, you too are an engineer. This is the thesis of this little book by Billy Von Cohen. Now, clearly, if you put design associated with engineering and design, they cover the whole front in there. But you also have science, social sciences, and humanities, which are connected with engineering. And engineering encompasses all of the thinkings. Chemie is not only in the middle of all engineering, but in the middle of all the university landscape as well. And the university landscape involves things like medicine, law, business, public policy, education. So let's go now to the modes of thinking, but kind of zooming in more on art, technology, and science. In science, science has been open source since the invention of journals like the Philosophical Transactions of the Royal Society. Standing on the shoulders of giants is a good strategy in science. That's how you build your arguments. In technology, the only reason to stand on the shoulder of an elder giant is to crash the elder giant, your technology to replace the previous one. And in art, it's a bad idea to stand close to anybody. Derivative is not a bad word in technology, but it is deadly in art. The time flows are also different. And this will make it clear. In here I have a series of paintings in between, it's about 80 years of paintings. And if I ask you to put an arrow of time, order them chronologically here, you will have a tough time, unless you have had a course in history of art. By the way, the upper left is the newest one, the lower left is the oldest one. So what you have in here, and this figure encapsulates a lot, is that technology builds over the past There are revolutions which are infrequent. Quantum mechanics would be one, relativity could be another one, the birth of molecular biology, another one. But if there are dead branches, they get trimmed. Technology is a continual adaptation with disruptions, and in art, is a constant reinvention. In modern and contemporary art, you cannot argue that there is progress. Before we went into abstract art and our art was representational, you could argue maybe that there was an arrow of progress. Not so anymore. So in mastering the domains, in science, you absorb and then you do. But in things like art, the same as in writing, music, the learning and doing are integrated. They are intertwined. You do not take courses on theory of painting 1 and theory of painting 2. You paint. So in a classical engineering program, as well as in every science program, there is consumption and then production and a capstone design at the end. But what is emerging and has been what we have been doing for the last 12, 15 years in Northwestern, as the consumption and production are intertwined, design is across the curriculum, and many courses connect grads and undergrads. You see courses in which it's common to see engineers, people from business school, people from the medical school, people from the law school, students from anthropology, sociology, all of these. A way of seeing this and the role of design as a cross-linking is you have science, technology, and art with the words discover, invention, creation. The left being the domains in which logical thinking, rational thinking, mathematical thinking, if you want, is what drives the things. And on the right, right brain thinking, which is divergent, metaphorical, aesthetic, if you want, creative. Of course, the brain is much more complicated than this, not that right brain domains concentrates on what I call here left brain skills. And this is a figure of speech, but it's a good way to see that when you put engineering plus design, you cover the whole spectrum in there. Now, let's look at now the interplay between science and technology. A lot of what chemists had to do was that when chemists arrived to the scene, chemistry was developed as a science, but the science that was needed to advance technology in chemical engineering was not developed. Physicists have been working on thermo, we have Gibbs, Boltzmann, but at some point the physicists decided, we are done with this. Someone has to advance in knowledge, the same as in catalysis, physical chemistry, and chemical engineers had to advance the missing pieces before advancing the profession. But this is not how all technology advances. We had steam engines way before the laws of thermodynamics were sort of established. The book by Sadi Carnot will remain even on the shelves without attracting any attention for several decades. The same thing with flight. I mean, we were flying before the equations that would allow you to calculate lift were developed. Ironically, some of that math comes from Lord Kelvin, who declared that heavy and air flying machines are impossible. But at some point, there are explosions in science. This is probably the meeting that had the most concentration of science in any conference in history. The names that you can see there, Planck, Curie, Dirac, Einstein, de Broglie, Heisenberg, Schrödinger, Bohr. These were the people who gave birth to atomic theory, among other things. And at some point, someone exploits that science, builds transistors, and someone comes with a logic and that can make all of this work. Claude Shannon in here, which is on amount of impact per recognition, he has to be one of the highest impact scientists people in the world. His degree was in engineering, by the way. He's the father of information theory. So at some point, it's easy to believe that flow occurs only this way, science to technology. And this is what got sort of codified by Vannevar Bush, arguably the most impactful dean in the history of engineering in the US, advisor to presidents. One of the organizations that he ran, the Office of Scientific Research and Development, was responsible for the invention of the radar, critical in World War II, and also the creation of NSF. That was a consequence of science, the endless frontier, this reporting here. So science implies understanding, and this understanding is what gives us the ability to predict things. But things are changing, and we need to be prepared, because the world now we can predict without understanding. And that's basically what is at the heart of AI. We can predict things in some domains without really understanding. Now, if you take a back view and look at the impact of engineering in the world, this is a partial listing produced 20 years ago by the National Academy of Engineering. These were the things that they were deemed the one, a subset of these. There are 20, I'm not listing all of them, that had the highest impact on society. And there are a few things in there that are connected with chemical engineering, like petroleum and petrochemical technologies, advanced materials. All of these things either came out after departments were created or even before they were created, okay? We had really steam power developed before they were really mechanical engineering departments. Certainly we had flight before aerospace was created. And so when you look at chemie in the spectrum of what's done in science and applied research, this is a classical 4-quadrant diagram poster by Pasteur. Not by Pasteur, is named the Pasteur quadrant because one of the quadrants used in inspired research is named after Louis Pasteur. So pure basic research without any consideration of use is Bohr, and pure applied research, applied without trying to understand things, is Edison. Now, chemie, I would argue, initially was more on the pure basic, advancing the frontiers of science, moving into technology, and now is moving more into the technology side there. But one thing that is interesting, looking at the recent past, not the really far away past, this observation comes from Bill Showalter. If you look at the citations that were written about people in chemical engineering, when they were elected to the National Academy of Engineering, you see the words understanding, elucidating. I am in that category, developing the foundations of something. Whereas in other parts of the academy, like electrical engineering or electronics, is for advances that move the frontiers of technology, contributions to signal and whatever. So another view, even of higher altitude, is the Draper Prize. I happen to have chaired this for a while, and this is like the Nobel Prize of Engineering. You see people who are recognized for inventing the World Wide Web, Fortran, integrated circuit, fiber optics. When you look at the chemie contributions, platforming, that's Val Hansel, medical drug delivery systems, this is Bob Langer, who altered the equilibrium of everything in chemical engineering. Directed evolution, this is Francis Arnold, who won the Nobel Prize of Chemistry. Francis is at Caltech. And Jean Fréchet and Wilson for chemical amplified materials for micro and nano fabrication. So a lot of the things come from things that were developed, we're still milking things of the solid state physics advances and computer science. And if you look at chemie on how we did, and by we, I mean me included, in 2007, I was part of this report. We said at that point, this is a while ago, 2007, we saw emerging some things, and we saw that some things were weakened, and some things were right. SynBio clearly has emerged, and at least here is completely driven by chemical engineering. But I don't think that we have so much emphasis now on fossil energy extraction. And I think that we should probably go more in the business of operational optimization. Now, let me give you two examples from two colleagues that are not chemists, but what they have done could be chemi or could be part of chemi. The first one is a fellow named Dirk Brockman. Dirk Brockman was here in applied mathematics, and eventually, before he went back to Germany in 2013, he co-authored this paper on epidemics. It also could be disruption of supply chains, transportation, with Dirk Helbing, also from Germany. And in here you have the interplay between networks, which is something that has got the attention of people in engineering, and in my own institution in engineering, and crossing to the business school. And clearly, when COVID hit, Dirk was completely prepared to be the central voice in Germany about anything that had to do with the spread of COVID. Now, we have people in chemi, Luis Amaral, who work on similar things. And I mention this because this is the interplay in between global networks and local things like the transmission. There are many problems that fit in this category. The second example, and it will look much better with music, is a video that was done for John Rogers. The video is about 7 years old now, and John works on wearable technologies, biointegrated labs. This involves material science, which has an appointment, biomedical engineering, has appointments in the medical school, but you will see that, for example, in this device that captures sweat and analyzes the composition and so on and so forth, this could be chemical engineering. This is something that chemists could be working on. It interacts in many ways with lots of components in the medical school, especially athletics, for example, detection of diseases before really the symptoms are visible. And this is something that could also be part of what chemists do. There's a lot on materials that could eventually implanted and dissolved without any consequences. So the whole point that I'm trying to make here is that the importance of having a broad view of things, a view that is broad enough to augment our lens and have consequences on how chemi interacts with other units. Let me stop here and give you some closing remarks after I move from my desk. Thank you. Okay, so happy to have had the opportunity to share my views. System thinking, as in process systems engineering, should be more widespread in the context of chemical engineering, but it's not. Chemi has been more aligned with material science, biology, chemistry, and medicine than with industrial engineering, systems engineering, logistics, and operations. Regarding my first example, Dirk Brockman and the paper on SARS, I have said before that the time is right for chemi to re-embrace and expand system thinking and capture new territories. A current confluence of factors, energy, global health, quality of life, all arising from increased interconnectedness and speed and complexity, makes the intersection of chemistry with complex system thinking significant and impactful. Regarding the second example, in bioelectronics, something that connects with really every engineering department on campus, I would look at possibly intersections with other departments and units in engineering, use connections, double and triple count people, but for that you need people who can be double and triple counted. In general, I would advise continue deepening the frontiers of science, but also to embrace entrepreneurship and technology transfer, and maybe involving some entrepreneurs in residence. But if there is one central message arising from the entire talk, is the importance of having a wide lens. That's the central message that I try to convey.